So just like we can count nails by weighing them in pounds, we can count atoms by weighing them in grams. And again, I jumped ahead of myself. Even if you could see atoms and counted them 24 hours a day as long as you lived, you'd barely be able to you'd barely begin to count the number of atoms in something as small as a grain of sand. Think about that. Non-stop counting. For the rest of your life, not even close to the number of atoms in a grain of sand. It's mind-boggling. So dozen is convenient for nails and donuts and lots of things in real life. But we need a larger number because it's too small to be useful. So we have a unit called the mole. M-O-L-E. It's not a small furry animal that burrows. It is also not a delicious sauce. It's just mole. M-O-L-E. Strangely enough, it has an abbreviation, M-O-L. I'm like, you can't just write the E, but there it is. So this we call the chemist's dozen. It is like a dozen. It's a particular number of things. The number is just really, really different than 12. The number is 6.022 times 10 to the 23rd. That's an incredibly big number. But atoms are incredibly small, and so this is a useful size for us. It's called Avogadro's number. It was named after the scientist Amedeo Avogadro, who lived back in the 17 and 1800s. So 1 mole, 1 chemist's dozen, is 6.022 times 10 to the 23rd things. You could have a mole of this, a mole of that, a mole of calculators, a mole of carbon atoms, a mole of sodium chloride formula units. It's just like a dozen. It's a number of things. So I do have to tell you a funny story. Well, maybe it's just interesting, not funny. So in October, chemists celebrate Mole Day on October 23rd. 10/23? October 23rd. Officially goes from 6:02 a.m. to 6:02 p.m. That's Mole Day. So my husband is a chemist. He teaches here as well. I'm a chemist. Our 4th child was born on Mole Day. Right? And he weighed 10 pounds, and he was 23 and a half inches long. 10/23 on 10/23. I missed the 6:02 part. I tried, but there's only so much you can do. So he's our mole baby. We actually did, for about 5 seconds, say, should we give him the middle name Avogadro? No, we're not going to do that. So we didn't do that. But he's my mole baby. How much is a mole? A mole of atoms, ions, or molecules is a reasonable quantity of stuff. This many pennies contains 1 mole of copper atoms. Okay, that's a useful size, right? You could stick those pennies in your hand. They're large enough to see, but not so big that it's going to be a problem to move them around or do something with them. These 2 balloons contain about a mole of helium atoms. Again, a useful quantity. Okay, so just like dozen is useful for counting bagels or eggs or donuts, the mole, 6.022 times 10 to the 23rd, is a useful number for counting atoms, molecules, and ions. Little teeny tiny things. So where did that number come from? It's defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. Now, do you remember hearing about 12 grams of carbon-12 before? When we talked about the definition of an atomic mass unit, it was 1/12 the mass of a carbon-12 atom, right? So 12 grams of pure carbon-12 is the mole. That's that 6.022 times 10 to the 23rd. The reason it was defined in this way is that it gives us a relationship between mass and numbers of atoms, and it also corresponds with the atomic mass of a single atom. So if we have moles and we want number of atoms, or it's similar to converting from a dozen to a number of nails. 1 dozen is 12 nails. 1 mole of something is 6.022 times 10 to the 23rd atoms. So if we have 9.5 times 10 to the 27 atoms, how many moles of atoms is that? We should write this out. When we do this in our heads, sometimes we do it backwards and get the answer wrong on the test. I don't know what is wrong with my stylus today, but it's making me crazy. Come on. Really? Try the other. Ooh. Well, I don't know if that's better. Yeah, it's better. Okay, that many atoms. I want moles. I'm going to have atoms in the bottom. Just like we did for a dozen nails is 12 nails. 1 mole is 6.022 times 10 to the 23rd atoms. Now, it's important to use scientific notation on your calculator correctly. So to do this, 9.5 EE27 times 1 divided by 6.022 EE23 equals. And my calculator is showing me 15775 point stuff. I can consider significant figures. This has 2 sig figs. As Avogadro's number is usually written, it has 4 significant figures. This is not an exact number. It is known to more decimal places, but we don't need to remember those, so we're just going to use 4. So this has 2 sig figs, this has 2 sig figs. So if I'm going to round this number to 2 significant figures, this is the number I am rounding to. The next digit is the decider. It decides if I round this one up or leave it alone. Because the next digit is 7, I'm going to round the 5 up to a 6. Get 1 6. And then these remaining 3 that come before the implied decimal point have to be replaced with zeros. So 16,000 moles. The better thing to do is to put it in scientific notation. Any questions? If you came up with a much larger number, it's because you're not entering your Avogadro's number using correct scientific notation, and your calculator thinks it's 2 different numbers, and it's actually multiplying by 10 to the 23rd instead of dividing. If that's happening to you, please come talk to me after class or during lab, and we'll straighten that out. Any questions? So how many gold atoms are in a pure gold ring containing 8.83 times 10 to the minus 2 moles of gold? Remember, 1 mole equals 6.022 times 10 to the 23rd things. Here, in this problem, the things are atoms. .83 times 10 to the minus 2 moles. I want atoms. So atoms go in the numerator. Moles go in the denominator. So the moles cancel out. 1 mole is Avogadro's number of atoms, like 1 dozen is 12 things. 1 mole, 6.022 times 10 to the 23rd. I often forget to leave enough room there. So 8.83 EE, negative 2, times 6.022 EE 23. This time I get a really big number. This result should have 3 sig figs. 5.3174 times 10 to the 22. atoms. Is that a reasonable number? Should we get such a huge number? Yeah, it's number of atoms. In anything, a ring is something that we could see. In anything that's large enough to see, there has to be a huge number of atoms. So when I round this, I get 5.32 times 10 to the 22nd atoms. Just like with the nails, counting by weighing is not counting exactly. But when we can't count exactly or don't want to take the time to do so, it's good enough. Any questions? Yes?
For example, if we have like, just for example, if it's like 5 6/6 for the 8.83, right? There's 5 6/6. Do we go to the 6/6 on the atoms?
That's a good question. So what if this had more significant figures, like 5 or 6 or 7 sig figs? Avogadro's number here only has 4 significant figures, so that would limit your answer. What we see in the problems is usually there's 2 or 3 sig figs, and so it's not a problem. So if you were doing research and you had more detailed information here, then you could look up and use more digits from Avogadro's number. It's a good question. Anybody else? So that's moles to numbers of atoms, but we still haven't gotten to mass. We need one more factor. So for nails, we needed the weight of 1 dozen nails. Well, how much does 1 dozen nails weigh? Then we can figure out how much, 5 dozen nails would weigh. For atoms, we need the mass of 1 mole, the mass of 1 chemist's dozen of atoms. And this is called the molar mass. So the molar mass is the mass of a mole. It's the mass of 1 mole of atoms of that element. And this is the same number as the atomic mass, but the unit is grams instead of atomic mass units. And this is not magic or some awesome coincidence. We set it up this way. Okay, that's why Avogadro's number is a weird number. Why not 1 times 10 to the 23rd? It would make the math easier. It's this way because Avogadro's number is the number of carbon-12 atoms in exactly 12 grams of carbon-12. The atomic mass unit is 1/12 the mass of a carbon-12 atom. So a carbon-12 atom weighs 12 atomic mass units. A mole of carbon-12 atoms weighs 12 grams. So atomic masses are on the periodic table. Molar masses of elements are also on the periodic table. They are the same number. You just use a different unit. The mass of a dozen, or the weight of a dozen nails, changes for different nails. Okay, there is a mistake in these pictures. Can you find it? Count the nails. The smaller one only has 11. The point of the picture is that it's 12 nails, and there's only 11. And what scares me probably the most is that when I looked at this picture, I noticed that. Anyway, so now it has 12 nails. Okay, so here's a dozen large nails and a dozen small nails. Which one weighs more? The large one. Those nails are bigger. They're made out of the same metal. They're all solid. There's no tricks here. The larger nails, a dozen of them is going to weigh more than a dozen of the small nails. And the same thing is true with atoms. Here we have 1 mole of sulfur atoms. That's going to weigh 32.07 grams. Here's 1 mole of carbon atoms. This only weighs 12.01 grams. Because these are like the small nails, and these are like the large nails. Each sulfur atom weighs 32.07 atomic mass units. one carbon atom on average weighs 12.01 atomic mass units. So if you have the same number of them and each of them weighs less, the overall amount is less as well. So molar mass is the mass of one mole. So it's different for different elements. 32.07 grams of sulfur is 1 mole of sulfur. It's Avogadro's number of sulfur atoms. 12.01 grams of carbon is 1 mole of carbon, Avogadro's number of carbon atoms. The number of atoms stays the same, but the mass changes. For lithium, it's only 6.94 grams. Molar mass is the conversion factor between grams and moles. Moles is the counting unit, the dozen, and grams is what we can measure, we can weigh. So calculate the number of moles of calcium in 91.4 grams of calcium. So these problems can be solved with dimensional analysis. So the number given is 91, oh wait, I don't want to write with that marker. 91.4 grams of calcium. And we want to know how many moles of calcium. This is like, okay, I have 5 pounds of nails. How many dozen nails is this? Well, I need to know how much 1 mole of calcium weighs. That number is on the periodic table right under the symbol for calcium. So I can go directly from grams to moles. The conversion factor is the molar mass. For calcium, 1 mole of calcium is equal to 40.08 grams of calcium atoms. So 91.4 grams of calcium. I have 1 arrow, and I have moles on top and grams on the bottom. 1 mole weighs 40.08 grams. So 91.4 divided by 40.08 equals 0. So this number that I'm starting with, the mass, has 3 significant figures. This, as I've written it, has 4, and so this answer would have 3. I've indicated the 3rd digit, and then I wrote 2 extras to avoid rounding errors. And so I get 2.28 moles of calcium. Yes? We don't need Avogadro's number here because, like with the nails, we're trying to find the number of dozens instead of the number of actual nails. So here we're trying to find moles, this large number of atoms instead of individual atoms. So we use moles almost exclusively. We very rarely, I mean, there will be calculation problems. You need to know how to convert between atoms and moles. But when we talk about doing actual experiments and things, we always talk about moles because number of atoms is always such a ridiculously large number, it's not useful. And that's why we have moles to start with. Find the number of grams of sulfur in 2.78 moles of sulfur. So the last problem, we had grams, we wanted moles. This is the opposite. We've got moles and we want grams. So 2.78 grams of sulfur, and we want to find out how many grams of sulfur that is. Yeah. Just seeing if you're paying attention. No, I don't know what I'm doing. Moles of sulfur. There we go. So the relationship between grams and moles is on the periodic table. We look on the periodic table, and under sulfur is the number 32.07. Grams of sulfur is equal to 1 mole. So I've got 2.78 moles times. I want grams on top this time and moles on the bottom. I don't have to think about, do I multiply, do I divide? The units tell me what to do. So I get the units in there, and then the units tell me where to put the numbers. 32 this time goes on top. 32.07 grams is 1 mole. So 2.78 times 32.07 equals. How many significant figures would the answer have? 3. So 89.154 grams. 89.2 grams. Any questions? So what if we did want to know how many carbon atoms? So say we have a diamond that weighs 0.58 grams. A diamond is carbon. It's just in a really cool form, but it's just carbon atoms. So 0.58 grams of diamond is 0.58 grams of carbon. So we've got 0.58 grams of carbon. And what do they want us to find? Atoms. Now, just like we could skip when we did the pounds and the nails, you can skip the using 1 dozen is 12 nails. You can substitute that in. You can do the same thing here. Let me write this at the bottom. So 1 mole, let me do this. So molar mass of carbon is 12.01. So 12.01 grams of carbon is equal to 1 mole of carbon. 1 mole of carbon is equal to Avogadro's number of carbon atoms.
Were we just supposed to know a diamond was carbon?
Not necessarily.
Okay.
I wouldn't expect you to know that on a test.
Okay.
Yeah. So 12.01 grams of carbon is 1 mole of carbon. That's on the periodic table. 1 mole of carbon is Avogadro's number of carbon, because 1 mole of anything is Avogadro's number of that thing. So we could do grams to moles to atoms. Grams to moles to numbers of atoms. That's the more, well, I don't know which way it is. The longer way for sure. Or you could say, well, I don't actually need to use the mole here because this is the mass of Avogadro's number of atoms, and so you could skip over that if you want to. I'm going to do it the long way, because if you like the skipping method, you can probably figure it out on your own. So 0.58 grams of carbon. I've got 2 arrows, so I've got 2 conversion factors. So first I'm going to go to moles, and then I'm going to go to numbers of atoms. I want moles down here to cancel those moles, and I want grams down here to cancel those grams. Okay? Um, 12.01 grams is equal to 1 mole. This is the molar mass. This goes in here. So 12.01 grams is equal to 1 mole. And then here, the relationship between atoms, the particles, and mole, the dozen, is Avogadro's number. So Avogadro's number of atoms is 1 mole. So 0.58 divided by 12.01 times 6.022 EE23 equals. Should have 2 sig figs. 2 times 10 to the 22 And the unit is atoms. When we round that, 2.9 times 10 to the 22 atoms of carbon. We should be getting a really, really big number like that. If you're ever calculating number of atoms and you get a negative exponent, that means you have less than one atom, and that's not possible. Like, how many people are in the room? 0.02 people. What? No, wait a minute, something's wrong. Any questions? Yes?
You would only be able to skip that 12.01 grams equals to 1 mole of carbon, just with carbon, right?
You can skip it in any calculation like this, because here in this unit, instead of writing 1 mole here, you could write what 1 mole means. You could write 6.022 times 10 to the 23rd atoms, because you could always replace 1 mole with Avogadro's number of particles. Mm-hmm.
So why'd you round the grams of carbon for?
This one?
Yeah.
Okay, because on the periodic table it gives more, right? So on this periodic table it says that the mass of carbon is 12.0108. Okay, that is a more precise number than what I used here, which is 12.01. Some periodic tables, just for convenience, have all of the masses rounded to 4 significant figures. This usually does not cause a problem in our calculations, because the numbers that we're measuring experimentally or that are given in our problems are 4 sig figs or fewer. So because I have a whole bunch of 4 sig fig molar masses memorized, I tend to just use those. Okay. It is always correct to use all of the digits on whatever periodic table you're looking at. If you compare lots of different periodic tables, you may notice that the numbers are not all exactly the same. That's because they get updated periodically. Sorry. The periodic table is updated periodically. Totally unintentional. Any other? Yeah.
How did we start with 23, like 10 to the 23rd, and end up with 10 to the 22?
That's a good question. So we've got 10 to the 23rd in here, and yet over here it's 10 to the 22. That's because when you take this number that's less than 1, 0.58, and you divide it by 12, you get a small number, and when you multiply it by 6, this number is still less than 1. And so that causes the exponent here to go down. If you do it without the 10 to the 23rd, just 0.58 divided by 12.01 times 6.022. You get 0.29 times 10 to the 23rd, and that's not proper scientific notation. So moving this over, then you drop that, but because we're going to use our calculators, we don't have to worry about doing that. But that's why. Any other questions? Calculate the mass of 1.23 times 10 to the 24th helium atoms. So 1.23 times 10 to the 24 atoms of helium. And the mass. Well, what mass unit do we usually use? Grams. We use grams. Well, how much does a mole of helium weigh? It's right on the periodic table. 4.003 grams of helium. So, do you want to go through moles, or do you want to take the shortcut? Pardon me? Well, we can go directly from atoms to grams, or we can go atoms to moles to grams.
Long way.
The long way? I'll do this. I'll do it both ways. So first we'll do it the long way. So this many atoms, and we're going to convert to moles, and then we're going to convert to grams. So I'm going to put atoms down here, and I'm going to put moles down here. One mole is Avogadro's number of atoms. And how do we know that it's 6.022 times 10 to the 23rd? Because we learn it, right? Just like we learned that a dozen is 12. 4.003 grams is 1 mole for helium. So we got 1.23 times 10 to the 24th divided by 6.022 times 10 to the 23rd times 4.003 equals.
Why did you put Avogadro's number in the front this time and not where it was last equation?
Why is it in the first fraction and not the second one?
Huh?
Because here we're going from atoms to moles and then moles to grams. In the previous one, we were going backwards. We were going from grams to moles and then moles to atoms. And Avogadro's number is the conversion factor between atoms and moles. So 8.1761 grams, yeah, or 8.18 grams. So that's doing it the long way. Any questions about that? So to do the short way, what I'm going to do is I'm going to say, well, 1 mole of helium is this mass, but I know that 1 mole of helium is Avogadro's number of atoms. So instead of saying 1 mole there, I'm going to say 6.022 times 10 to the 23rd atoms. This is like, instead of writing 1 dozen nails, I'm going to write 12 nails. So then I'm going to do 1.23 times 10 to the 24th atoms. Now I have a relationship directly between atoms and grams. So I can put grams on top, atoms on the bottom. 4.003 grams, 6.022 times 10 to the 23rd atoms. The atoms cancel out. The numbers are the same. We just got rid of these ones. So it's this divided by that times this. We're going to end up with the same answer. The best way for you to do it is the one that makes sense to you that you can remember how to do. Okay? Any questions?
So when you multiply, you have to put it right there.
You need the EE button. Yeah, you got to use the EE button. So be sure to do these calculations on your calculator, and if you're not getting the correct answer, then come talk to me, because you've got a glitch in your communications with your calculator. And I can help you fix that, and that'll cause you to score much better on the exam. How big is Avogadro's number? So we said 22 pennies is Avogadro's number of copper atoms. If you had that many pennies, if you had Avogadro's number of pennies, it would cover the Earth's entire surface to a depth of 300 meters.
What does that mean?
What?
I can't picture it.
It is hard to picture. Okay, so 300 meters. Meter doesn't really mean much to us. Meter is like a yard. So 300 meters is roughly 3 football fields from end zone to end zone. So think 3 football fields tall, the entire surface of the Earth covered in pennies that deep. What? Can you picture that?
Yeah.
Huge, right? So, think about sugar. A crystal of granulated sugar, that's the stuff you have at home in the sugar bowl. It has a mass of less than a milligram, a diameter of less than 0.1 millimeter. Little teeny tiny thing, right? If we had a mole of sugar crystals, those little things, it would cover the state of Texas to a depth of several feet. Texas is very large, on the same order as California. Think of California covered in sugar several feet deep. Is that a lot of sugar crystals? It's a heck of a lot of sugar crystals. Okay. Avogadro's number is so big that we just can't even begin to understand how big it is.